Hi, everybody. Good afternoon. My name is Hongyi Su. I'm coming from Fudan University in China. And first of all, I would like to thanks to Professor Liu inviting me come here, and thanks for your generous sharing with your ideas, and my research benefit a lot from your Liutex research. So what I want to present here is basically 4 topics. First, we built a very large-scale turbulence DNS database, and the rest of the 3 components of research are basically supported by this database, turbulence database. So giving you just some background on the research, as we know, we getting into the AI era, and which fundamentally almost changed our way of doing research. And the science, big data are at the foundation of these AI for science campaigns, as you know. So we will see a lot of strong interactions between the AI and I would say BI. So basically brain intelligence. Mostly the BI accomplish the 1 to 0 tasks, and AI will quickly push it into from 1 to 10 and even 10 to 100. So within the scenario of fluid science, we will say we are very scarce about the reliable science big data. And the second thing is our theoretic framework still stay very classical. Basically, our Freud ancestor laid out those framework for us. And so our solution 1 is to build a very big science data. And this data include a fundamental full configuration for channels, duct, etc. And we quickly push these things into a multi-wing representative type of aerospace external flows and the internal turbulence inside the blade channel in a compressor or turbine. The second solution is basically from 0 to 1, which is inspired by Professor Liutex, Professor Liu's Liutex. Basically, we rethink about revisiting this kinematic part of fluid mechanics from Cozy stocks to the triple decomposition. And by doing this, we revisiting the constitutive relation and rewriting the fluid dynamics equation, which is basically Navier-Stokes. And we call these corrected Navier-Stokes. So this is our corrected Navier-Stokes equation. Basically, it's corrected by these stretched tensors. I'm going to give details later. So the second part of research, which is, we called it from 10 to 10, 1 to 10 type of research is the war law development. In this part, we first, following the footprint of von Karman law of the war, we further push it to the universal war law models. And I'm going to give details for war-bounded turbulence. And we try to apply this war law model to the type A, which is basically a flat plate turbulence. And we got these, the law representations for the entire turbulence boundary layers, not just the semi-log and the viscous linear. Then the next object is try to push these war law relations for the separation regions, which is really a breakthrough by making use of Liutex theory. Maybe I'm going to give my ideas later on. So the third part is we try to address the industrial concerns and by renovating the Rance closure model using our using our DNS database. Basically, we insert the renal stress as a source term to close the Rance model and solve the mean flow field. Okay, so have a look at these, just to give you a general idea about this is our channel flows database. And here is the multi-win type of external flow configurations. And here is the flow inside the blade channels. You can see a lot of turbulence event on these, on both these. This is the suction, and this is the pressure. These are all demonstrated by the Liutex isosurface. So on this side, you can see the evolution of lift coefficient, the drag coefficient, with the changing of the turbulent flow on the airfoils. Okay, so this is basically give you the general idea of our database. And once we get this data built, and then we started to dig into the fluid dynamic side. And for the kinematic side, I do not need to go to details because Professor Liu already did that part very good. So basically here I would like to comment is Liutex theory allow us from the Cozy-Stokes level of decomposition go into one more levels to a more fundamental kinematics, like a very pure type of motions of shearing, stretchings, and rotations. So now we know this very well. The next thing we want to do is the flow dynamics. So see whether these decomposition can give us some new idea in the dynamic development. So when touching the topic on flow dynamics, the first thing we think is the constitutive relation, right? It is very legitimate for Stokes to include the shear deformation into the constitutive equation based on this very classical fluid experiment done by Newton, right? It's called the Newton's friction law. But however, when we consider if these components need to go into the current Newtonian fluid constitutive relations, we cannot find any experimental support on this for over 200 years. We did a lot of search on this part, and the only reason this part go into the constitutive relations is because Stokes makes the isotropic assumption, which basically means the stretching motions is performed exactly as the shear motions. So whether this assumption is legitimate or not is a very, very big question. And the second thought on this term, by seeing these forms, it reminds me with the Hooke experiment on the spring. He developed this Hooke law, right? This basically the force proportional to the displacement by a coefficient. And this is exactly the same scenario in fluid dynamics. And therefore, it looks very much like this force is a plastic force. Can we imagine that a plastic force can exist in the fluid motions? I leave that question to you. You can have a double think. And therefore, try to resolve these issues, at least interrogate it by adjusting the Navier-Stokes equation and by taking these components off from these fluid dynamic equation. I don't have the time to go to that mathematical detail, but general idea. So we come up, inspired by the Professor Liu's idea, we have to do this in the eigenvector direction, whether it is 1R or 3R, which is 1 real or 3 real, we consider this into two situations. Therefore, you can see when the flow rotating, we have a correction for false terms is like takes these tensor forms, which is very similar to Reynolds stress tensor. But it is the unit component product form. And for the 3 reals, also it is a shear vector component product form. So once this form is derived, and then we want to test it, give some numeric evidence. So the first thing we did is we performed DNS on these equations and check it, compare it with the conventional or traditional Navier-Stokes. I'm going to show you here just with 2 colors. So this is very simple. Blue color, oh, sorry. How to go back? The blue color means 1 real, and the red color means 3 real. Here, the left side is corrected Navier-Stokes. The right side is traditional Navier-Stokes. We can see some structural difference between these 2 equations. That means we have some large-scale differences. Then we can see basically this 1 real and the 3 real, they are equally important because they almost occupy half and half region of the fully developed regions. So that is just a qualitative observation. Now we get to the quantitative. We take the statistics of Reynolds stress and the mean flow field from this channel flow. And then we can see, we use the Moser and Lee. He gives very accurate channel data. And this is green, one is Moser. And here we have our Navier-Stokes is, traditional Navier-Stokes is blue dot. And the red colors are the corrected Navier-Stokes. And as you can see, our data basically the corrected Navier-Stokes give a solution consistently approach to more accurate DNS data. That means our correction at least is on the right track towards the real solutions. Another comment is our corrected NS data gives exactly the von Karman constant. This is very commonly accepted. And here, Moser's data tend to give lower von Karman constant, which probably is associated with the inclusion of the normal stress terms. So that's our guess at this moment. Okay, that's the first part. The second part is the universal rollout model. For this part, we basically follow the footprint from von Karman. He used the so-called local frictional velocity scale to develop this law of the world. Here, we introduce the so-called ensemble averaged frictional velocity scales. And by using these scales and the associated length scale and the time scale, and we renormalize Navier-Stokes equation, we can find suddenly this equation, there is no Reynolds number. There is no Prandtl number. So that means the solution of this equation, the dimension has been significantly reduced from 4 to just the space and spatial, the time and the space. So this is very promising, I would say. And we apply this model to the flat plate, as you can see here. We are not the first using this indicator function. People in the DNS community have used this just for the semi-log regions. And we push this back into the more near-world layer. We use this function to quantitatively define the so-called turbulent sublayers. So we identify this second derivative 0 point is the viscous linear layer. And the first order derivative 0 is the inner layer. And then we define the entire sublayer. Once we do that, and we we find a kernel function, which is very important in restoring the analytic solution of velocity profile. This is the form of the kernel function, which is basically a Van der Waals damping function. And by using this Van der Waals damping function on these different layers, and we recover the entire turbulent boundary layer analytically in different sublayers. And these are the analytical solution expression, I would say, for different sublayers. And even more than that, once we recover the profile for U component, then we use the same idea for V velocity that is perpendicular to the wall. So again, we try to find two indicator function and then define these each turbulent sublayer for the V velocity, and then use the kernel functions to recover these turbulent velocities. So basically, we flat wall turbulent boundary layer, we find the complete wall law for this type of TBL. Okay, now let's see. We go back to the models. We see why this is a universal wall law, because this is directly based on the Navier-Stokes equation. So it has no restriction of turbulent boundary layer. We can push it even further to separating flows, right? So therefore, our next target is to go back to our DNS database. First, I want to show you the accuracy of this database. You can see a lot of detailed turbulence event there. These are represented by Liutex isosurface. This is one picture and another picture. Then, as you can see, by the conventional turbulent boundary layer analysis, we use the shape function to exactly recover the transition point. That's the paper we published in the Journal of Turbo Machinery recently. And here is on the pressure side. Therefore, you can see a lot of details. Then we go into these data, we find there's a very distinctive phenomenon in this compressor blade channel, which we call laminar separation bubble, LSB. And because we have a big data, we have different Reynolds number. You can see these LSB, they occupy different zones. But if we use the so-called frictional velocity scale to rescale these data, it is very promising. We can find a universal structure for this LSB. That's our next plans. So now, getting to the point of industrial application. We know in industrial application, the central issue is the turbulence closure model, right? So now we try to use the DNS statistics of Reynolds stress and insert this as a source term to close this equation. And by solving this closed equation, we can get a very accurate averaged flow in the Reynolds average sets. That is, you can see, we try this for the square annular duct. We use these Reynolds stress models to close this equation and then recover the mean flows with the very distinctive turbulence-driven secondary flow. Also, we pushed it into the industrial application. That is, we try the turbine blade. This is the Reynolds average solution part. So with this all being said, I reached the conclusion of this, my presentation. I do not need to reread it. I would be very happy to share the relevant reference with you if you are interested. Thank you.